Hello there, and welcome to The Sleepy Scientist, a quiet corner of the universe where science meets serenity, and every night we drift through the wonders of existence together. Here we explore the mysteries of space and time, not to rush through facts, but to let them wash gently over the mind, like waves of curiosity and calm. Tonight, we turn our gaze toward one of the universe's most mesmerizing enigmas: black holes. They are the quiet giants that shape galaxies, bend light and slow time itself. Invisible, yet all-powerful. Silent, yet responsible for the grandest designs in the cosmos. In this long, soothing journey, we'll drift through 100 fascinating facts about black holes, each one a window into their mysterious nature. You'll learn how they form, how they shape the stars, and why, even in their darkness, they hold some of the brightest truths of the universe. So, find a comfortable place. Let your mind relax, your breathing slow, and your thoughts wander freely among the stars. And as you settle in, don't forget to subscribe to The Sleepy Scientist, where we explore the most peaceful side of science, helping you rest, dream, and drift into the infinite calm of space. Now, let's begin. In the vast quiet of space, where light drifts endlessly and time itself seems to slow, there exist regions so mysterious that even the brightest minds can only describe them in whispers. Tonight, we'll journey into one of the universe's most fascinating creations, the black hole. These cosmic enigmas are not monsters, not destroyers, but elegant outcomes of gravity taken to its purest extreme. Each one is a silent symphony of physics, a boundary where our understanding fades and wonder begins. You're listening to Sleepy Scientist, where curiosity meets calm. If you enjoy exploring the universe while drifting into rest, take a moment to subscribe, and then let's begin our quiet descent into the dark beauty of black holes. A black hole begins its life as a star much like our sun, but far larger, heavier, and more intense. Deep within, nuclear fusion pushes outward while gravity pulls inward, a perfect balance maintained for millions of years. But when the fuel is exhausted, that balance shatters. The outward pressure fades and gravity wins. The entire core collapses inward, faster and faster, until all the matter falls into a point so small it defies measurement. In that collapse, a black hole is born, not a hole, but a region where the curvature of space becomes so steep that escape becomes impossible even for light. At the heart of every black hole lies a singularity, a point where density becomes infinite and the known laws of physics break down. It is not a physical surface, but a mathematical inevitability, where our equations no longer describe reality. Around it lies the event horizon, the invisible boundary marking the edge of no return. Once crossed, nothing, not light, not information, can escape. To an outside observer, an object approaching this boundary appears to slow, fade, and freeze, trapped forever in suspended time, though in its own frame, it falls inward without hesitation. The formation of a black hole can occur in several ways, but the most common begins with the death of a massive star. When nuclear fuel runs out, gravity crushes the core, and the outer layers explode outward in a supernova. What remains collapses further until the escape velocity exceeds the speed of light. Some black holes, however, were never stars. They may have formed from dense early universe conditions, primordial black holes forged before galaxies even existed. Others grow by consuming gas, dust, or even other black holes, increasing their mass across eons. In the center of our Milky Way galaxy resides one of the most studied black holes in the universe, Sagittarius A. It is about 4 million times more massive than the Sun, yet it fits within a space smaller than our solar system. Despite this immense gravity, our planet orbits safely tens of thousands of light years away. The motions of stars near Sagittarius A were what revealed its existence. They whip around an invisible point at tremendous speeds, guided by gravity stronger than any visible object could produce. Black holes come in different sizes, from the relatively small stellar mass black holes, a few times the Sun's mass, to the supermassive giants found in galaxies. There may also exist intermediate black holes, a missing link between the two, though they remain difficult to confirm. The smallest possible ones, perhaps formed just after the Big Bang, would evaporate through a process known as Hawking radiation, a faint energy loss caused by quantum mechanics itself. Over unimaginable timescales, even black holes are not forever. When matter approaches a black hole, it doesn't fall straight in. Instead, it spirals inward, forming an accretion disk, a whirlpool of gas and dust heated to incredible temperatures by friction and gravitational energy. The result is one of the brightest phenomena in the universe. Paradoxically, regions around black holes can be more luminous than entire galaxies, shining across billions of light years. The energy released is so immense that jets of particles can erupt from the poles, propelled by magnetic fields in a spectacle of cosmic power. Despite their reputation for destruction, black holes play a crucial role in the structure of galaxies. They act as anchors, stabilizing the orbits of billions of stars. The relationship between a galaxy's mass and its central black hole ES size suggests they evolved together. When the black hole feeds actively, it releases radiation and winds that regulate star formation, preventing galaxies from growing too quickly. Far from being cosmic monsters, they are guardians of balance in the architecture of the universe. The idea of a black hole was once only theoretical. It originated from equations developed by Carl Schwarzschild in 1916, soon after Einstein published his general theory of relativity. His solution described a point mass so dense that even light could not escape its gravity. For decades, scientists debated whether such an object could truly exist. It wasn't until observations in the 20th century, X-ray emissions, stellar movements, and eventually gravitational waves, that the evidence became undeniable. The mathematics had described reality long before we could see it. The first strong evidence of a black hole came from a system called Cygnus X1, discovered in 1964. It emits powerful X-rays from a compact object drawing matter from a nearby star. The orbit of that star showed the invisible companion must have a mass too large to be a neutron star. The only remaining explanation was a black hole. It was a moment of scientific humility. Something once considered purely theoretical had become physically real. Today, Cygnus X1 still shines faintly across the galaxy, its invisible gravity a beacon for our understanding. Even though black holes are invisible, their presence can be detected through their influence on light and matter. When they warp space-time, light bends around them in arcs and circles, creating effects known as gravitational lensing. Sometimes entire galaxies appear distorted because of a black hole's gravitational magnification between them and us. Through this lensing, astronomers can not only confirm their existence, but also map their environments, turning invisibility into measurable evidence. Time behaves differently near a black hole. According to Einstein's theory of general relativity, the stronger the gravity, the slower time passes relative to distant observers. Near the event horizon, gravity is so intense that time effectively comes to a halt for anyone watching from afar. This means if you were to observe someone falling into a black hole, you would never actually see them cross the event horizon. They would appear frozen, fading slowly into darkness as their light is stretched into longer and longer wavelengths. Yet for the falling observer, time feels normal, and the crossing happens in an instant. The difference is not illusion, but a consequence of space-time itself being warped by gravity. Near the edge of a black hole lies one of the universe's most extreme environments, the region where light and matter orbit at nearly the speed of light. This boundary is sometimes called the photon sphere. Here, light can circle the black hole several times before escaping or being captured. If you could hover safely near this region, you would see distorted reflections of the universe in every direction, a hall of mirrors made from gravity. Every photon, every ray of light would be trapped in an endless ballet of curvature, showing you the cosmos from countless angles all at once. Inside the event horizon, our known physics ceases to provide clear answers. According to relativity, space and time switch roles. Instead of space moving through time, time itself leads inevitably toward the singularity, and escape becomes as impossible as traveling backward through time. Nothing within that boundary can avoid the fate of falling inward, though we cannot observe this directly. Whether singularities truly exist as infinite points or are smoothed out by unknown quantum effects remains one of modern physics' greatest mysteries. Even now, new theories attempt to reconcile these paradoxes. Quantum gravity, string theory, and loop quantum cosmology all seek the missing explanation. Black holes come not only from collapsing stars, but also from cosmic mergers. When two black holes orbit one another, they gradually lose energy through gravitational waves, ripples in space-time that carry information across the universe. As they spiral closer, the waves grow stronger until they collide and merge into a single, larger black hole. The energy released in that final instant can exceed the power of all the stars in the visible universe combined, if only for a moment. These mergers are invisible to the eye, yet detectable through the faint stretching and squeezing of space itself, recorded by instruments like LIGO and Virgo. In 2015, the Laser Interferometer Gravitational Wave Observatory detected such a ripple for the first time, confirming a century-old prediction of Einstein's. It was the collision of two black holes over 1 billion light-years away. The signal lasted less than a second but opened an entirely new way of observing the cosmos. No telescope could have captured it. Instead, it was the vibration of space reaching Earth after traveling across the universe. That tiny distortion told us not just that black holes exist, but that they move, collide, and evolve in ways we had only imagined. When matter is drawn toward a black hole, it doesn't vanish instantly. Friction and magnetic fields cause it to heat and spin, forming immense jets that blast out from the poles at nearly light speed. These jets extend for thousands of light years, visible across galaxies as bright radio and X-ray emissions. Ironically, the regions around black holes, not the holes themselves, are among the most radiant in the universe. The process transforms gravitational potential energy into electromagnetic light, proving that even near total darkness, energy finds a way to shine. Supermassive black holes like the one at the center of the Milky Way often lie dormant, but in some galaxies, they become hyperactive. When they feed on surrounding gas, they create quasars, dazzling beacons that can outshine their entire host galaxies. Some of these quasars are so distant that their light began traveling toward us before Earth even formed. Through them, astronomers look back in time to the early universe, studying how the first massive black holes grew and how galaxies evolved around them. For decades, the idea of photographing a black hole seemed impossible. Black holes do not simply swallow everything forever. According to Stephen Hawking's groundbreaking theory, they emit faint radiation due to quantum effects near the event horizon. This Hawking radiation means that black holes can slowly lose mass and energy over incomprehensibly long timescales. The smaller the black hole, the faster it evaporates. A stellar mass black hole could last trillions of years, while tiny ones might vanish quickly. In this way, even the darkest regions of the universe are not eternal. They fade, release energy, and return their matter to the cosmos. If black holes can evaporate, then information must somehow escape. But how? This is known as the black hole information paradox. In quantum mechanics, information about the state of matter should never be lost. Yet inside a black hole, it appears to vanish. Resolving this paradox is one of the greatest challenges in physics. Some theories suggest that information might be encoded on the surface of the event horizon itself, leading to ideas like the holographic principle, the notion that our universe could, in some sense, be a projection of information stored on a distant boundary. Despite their invisible nature, black holes reveal themselves through motion, heat, and the dance of gravity. Around some, gas and dust swirl in vast glowing disks that emit powerful X-rays detectable from millions of light years away. This radiation arises not from the black hole itself, but from matter just before it crosses the event horizon, heated to millions of degrees. It is the universe's final shimmer before complete darkness, the farewell light of matter that will never be seen again. For astronomers, these luminous whispers offer a way to map the unseen, proving that what cannot be observed directly can still leave a trace through its influence on the visible universe. The 2019 image of the black hole in galaxy M87 was more than a picture. It was a bridge between imagination and reality. To create it, telescopes across the world synchronized with atomic clocks, forming one Earth-sized observatory. The data was gathered over several nights, carried across oceans on physical drives, and then combined using algorithms that reconstructed the shape of light bent by gravity. The result was a circular ring surrounding a dark core, the shadow of the event horizon. That faint ring was not just light. It was proof that Einstein's equations still hold true even at the edge of reality. To understand the energy near black holes, one must think not in terms of destruction, but transformation. As matter falls inward, gravitational potential energy converts into motion and heat. The closer it spirals, the more energy it releases. The disk glows across wavelengths, visible light, X-rays, gamma rays, until it reaches temperatures that would vaporize any known material. The brightness near an active black hole is so intense that it can push away surrounding matter, shaping the evolution of entire galaxies. The balance between gravity and radiation becomes a conversation of forces that never truly ends. Not all black holes are supermassive giants. Some are much smaller, scattered across the Milky Way as remnants of ancient stars. These stellar mass black holes may drift silently for billions of years, unseen except for when they interact with other stars. When a companion star orbits too close, the black hole's gravity strips gas from its surface, forming a glowing disk visible through X-ray telescopes. Many of these systems pulse and flicker, their brightness changing as they feed. Each one tells a quiet story of balance, the pull of gravity, and the release of energy, repeating endlessly in the dark. Black holes also shape their surroundings in subtle ways. Even when dormant, they influence the motion of stars across light years. Their gravitational presence stabilizes orbits and defines the structure of stellar clusters. In the early universe, growing black holes may have acted as seeds around which galaxies coalesced, pulling together the matter that would later ignite into billions of stars. The cosmic web that connects galaxies across the universe may have been sculpted, in part, by these gravitational wells. Without them, the large-scale order of the cosmos might look entirely different. When two black holes merge, the process is not chaotic, but surprisingly elegant. They orbit each other in ever-tightening spirals, each wave of gravitational energy carrying away angular momentum. The frequency of these waves rises until, in the final instant, they combine in a smooth crescendo, producing a single, larger black hole. The new object rings like a struck bell, radiating away imperfections until it settles into stability. These vibrations of space-time carry across the cosmos, and by studying them, scientists can learn about the mass, spin, and even the distance of the merging pair. The universe communicates through ripples in its very fabric. The detection of gravitational waves has given humanity a new sense of hearing. Traditional astronomy relies on light, but gravitational waves travel undisturbed through dust, gas, and time. They offer a direct line to the most violent events in existence, yet what we hear from them is not sound. It is a pattern of space itself, stretching and relaxing. Each signal recorded on Earth begins as a collision that may have occurred billions of years ago, carrying information about places we could never reach and times long before life began. In those fleeting tremors, the universe shares its hidden symphony. While some black holes feed voraciously, others exist in quiet isolation. A black hole that has consumed its surroundings becomes effectively invisible. It drifts through space, cold and dark, detectable only through its gravitational tug on nearby stars or its influence on cosmic dust. There could be millions of such silent travelers in our galaxy alone, unseen, yet shaping the paths of visible objects around them. These quiet wanderers remind us that the most powerful entities in the universe can also be the most tranquil. On rare occasions, a wandering star passes too close to a massive black hole. The tidal forces tear it apart in a violent process known as a tidal disruption event. The star is stretched into long streams of plasma that spiral inward, creating a burst of radiation so bright it can outshine the galaxy for months. What was once a stable fusion engine becomes a ring of glowing gas, its atoms scattered into the black hole's surrounding disk. It is destruction, but it is also rebirth. The material becomes part of a new cycle of energy and light in the cosmos. Black holes also act as natural laboratories for testing the limits of physics. They allow scientists to study conditions of gravity, temperature, and density that cannot be replicated on Earth. Observations of their surroundings help refine theories about how the universe behaves under extreme curvature. By comparing data from black holes with the predictions of general relativity, physicists have confirmed Einstein's ideas with astonishing precision. And yet, the closer we look, the more questions arise about information, quantum mechanics, and the unification of forces. The darkness around a black hole is not emptiness. It is an open frontier of discovery. Black holes are not solitary actors. They play a central role in the grand design of galaxies. At the heart of nearly every large galaxy, astronomers have found evidence of a supermassive black hole, often millions or even billions of times heavier than the Sun. These giants are deeply entwined with the growth of their host galaxies. When they accrete material, they release vast amounts of energy that influence the gas surrounding them. This energy, carried by winds and radiation, regulates the pace of star formation. In this way, black holes and galaxies evolve together, each shaping the destiny of the other in a cosmic relationship that has lasted billions of years. The connection between the size of a galaxy and the mass of its central black hole has become one of astrophysics' most remarkable patterns. This relationship, known as the M-sigma relation, shows that the larger and more massive a galaxy's central bulge, the larger its black hole tends to be. It suggests that galaxies and their black holes grow in harmony rather than independently. The mechanisms are still being explored, but many scientists believe that feedback from the black hole, in the form of radiation and winds, keeps the surrounding gas from collapsing too quickly, maintaining equilibrium between creation and control. Active galactic nuclei, or AGN, are galaxies where the central black hole feeds vigorously, shining brighter than all their stars combined. The matter falling into the black hole forms a disk so hot that it emits across the electromagnetic spectrum, from radio waves to X-rays. In some cases, powerful jets of particles burst outward from the poles, reaching far beyond the galaxy itself. These outflows carry energy into intergalactic space, influencing gas clouds light years away. The spectacle of an active nucleus demonstrates how gravity, the quietest force, can produce some of the loudest displays in the universe. Quasars are the most extreme form of this activity. They are young galaxies whose central black holes consume matter at extraordinary rates, producing radiant beacons that can be seen across the observable universe. Light from some quasars has traveled more than 12 billion years to reach us, carrying a message from an era when the first galaxies were still forming. Through these distant signals, astronomers can study how black holes shaped the early cosmos, how they heated intergalactic gas, slowed star birth, and seeded the large-scale structure we see today. Each quasar is a memory of the universe learning to shine. The jets emerging from active black holes are among the most mysterious structures ever observed. Composed of charged particles accelerated to near light speed, these jets can extend for thousands, even millions of light years. Despite their brightness, the exact mechanism that forms and sustains them remains uncertain. Most models suggest that twisting magnetic fields extract rotational energy from the black hole itself, converting spin into motion and light. The result is a stream of plasma so coherent that it travels nearly straight across intergalactic distances, a thread of order woven into the chaos of space. While these cosmic outbursts seem violent, they are also part of a larger harmony. The energy ejected by feeding black holes helps regulate the amount of gas available for star formation, preventing galaxies from collapsing under their own weight. This self-regulating cycle keeps galaxies balanced for billions of years. Without it, galaxies might grow too quickly, exhausting their fuel and fading prematurely. The universe thrives not only on creation, but also on restraint, and black holes are those silent arbiters of that equilibrium. The black hole at the center of our own galaxy, Sagittarius AI, is currently quiet compared to distant quasars. It feeds very little, drawing only small amounts of gas and dust from its surroundings. Occasionally it flares briefly, releasing bursts of X-rays before settling again into calm. Even in dormancy, its gravitational influence governs the orbits of stars in the galactic core. Astronomers watch those stars move in precise ellipses, completing orbits every few decades. From their motion, the mass and location of the black hole can be calculated, confirming its role as the Milky Way's anchor. When seen in infrared light, the region around Sagittarius A is a ballet of stars moving at breathtaking speeds. One particular star, known as S2, passes within a few light hours of the black hole at speeds exceeding 16 million kilometers per hour. Its motion provided direct evidence for the immense mass hidden in such a small volume. Observing this dance allowed scientists to test general relativity in conditions of extreme gravity. Each orbit becomes a slow experiment, showing how time, space, and light behave near the threshold of the unknown. Far beyond our galaxy, even more colossal black holes exist. Some, like the one in galaxy TON 618, possess masses equivalent to more than 60 billion suns. Their event horizons could engulf entire solar systems. Yet, despite their scale, the physics remains the same. Gravity curves space, light bends, and energy flows outward as matter spirals inward. From the smallest stellar black hole to the largest galactic titan, the same rules govern their nature. This consistency across unimaginable scales reminds us of a quiet truth. The universe is vast, but its language of physics is universal. At the edges of the cosmos, supermassive black holes act as anchors for the largest known structures, galaxy clusters, and filaments stretching across millions of light years. Their energy shapes the temperature and motion of intergalactic gas, influencing regions so vast that they defy comprehension. When multiple galaxies collide, their central black holes may eventually merge as well, releasing waves that echo through space-time. These immense interactions show that black holes are not isolated curiosities. but integral components of cosmic architecture. They are the silent engineers of order within apparent emptiness. Gravity is often imagined as a pull, an invisible thread that tugs at all matter, but in truth, it is geometry, the curvature of space and time itself. Black holes represent the most extreme expression of this curvature. They do not pull objects in like magnets. Instead, they reshape the landscape of space-time so steeply that all paths lead inward. In the presence of a black hole, the straightest possible line bends upon itself, and time flows in direction we can barely describe. This realization transformed our understanding of the universe. Gravity is not force, but form. Time near a black hole behaves in ways that defy intuition. To a distant observer, clocks near the event horizon appear to tick more slowly, stretched by gravitational time dilation. But for someone close to that boundary, time feels normal. It is the rest of the universe that seems to rush ahead. This effect is not illusion, but reality, a measurable difference caused by space-time's warping. In a sense, black holes are natural time machines, allowing us to witness how deeply intertwined time and gravity truly are. The photon sphere, a region surrounding a black hole where light orbits in perfect circles, is one of the most haunting ideas in astrophysics. A beam of light caught in this orbit would travel endlessly, neither escaping nor falling inward, tracing the edge of darkness in an eternal loop. For an observer, this creates a distorted and beautiful sight, multiple reflections of the universe overlapping, light curved upon light. This region marks the threshold between visibility and total absorption, a shimmering boundary where physics and perception merge. If a person were to fall toward a black hole, their experience would be profoundly different from what distant onlookers would see. From the outside, they would appear to slow, fade, and freeze just before the event horizon, their image stretched by gravity and red-shifted into invisibility. From their own perspective, however, they would cross the horizon without noticing, drawn inevitably toward the singularity. The difference between these two realities reveals a deep truth of relativity, that time and experience depend entirely on one frame of reference. Rotating black holes, known as Kerr black holes, add another layer of complexity. Their spin drags space-time around with them in a phenomenon called frame dragging. This means that near such a black hole, space itself begins to rotate, pulling anything nearby along in its flow. Within a region called the ergosphere, no object can remain still relative to the distant stars. Everything must move with the rotation. Theoretically, this effect allows energy to be extracted from the black hole ES spin, a process that might one day power technologies or explain the formation of cosmic jets. The mathematics describing a rotating black hole also predicts the possibility of paths through space-time known as wormholes. These hypothetical tunnels could, in theory, connect distant regions of the universe. Although purely speculative, they capture the imagination because they emerge naturally from Einstein's equations. Whether such passages could ever exist physically remains uncertain, but their theoretical presence suggests that black holes might hold secrets not just about gravity, but about the fundamental fabric of the universe. A non-rotating black hole is described by the Schwarzschild solution, a precise mathematical model discovered just after Einstein published his theory of general relativity. The elegance of this solution lies in its simplicity. It defines a spherical region where escape velocity exceeds the speed of light. Its discovery more than a century ago proved that black holes were not science fiction, but logical outcomes of nature, aka equations. Every modern observation of black holes, from gravitational waves to accretion disks, continues to confirm Schwarzschild ES insight, a timeless reminder that abstract thought can reveal the universe as deepest realities. The concept of entropy, usually associated with disorder, finds profound meaning in black holes. According to theoretical physics, the surface area of a black hole CES event horizon is directly related to its entropy, a measure of information hidden within. This idea, known as the Bekenstein-Hawking formula, implies that the more massive a black hole becomes, the more information it can store. Paradoxically, the ultimate void may also be the ultimate archive, holding the record of everything that has ever fallen inside. The question of how that information might be preserved remains one of science's most beautiful mysteries. The study of black holes has bridged the gap between the very large and the very small. On one side lies general relativity, describing gravity on cosmic scales. On the other lies quantum mechanics, governing the behavior of particles and energy. At the singularity, these two frameworks collide. Neither can fully describe what happens there, which is why black holes are often called the laboratories of the impossible. By studying them, scientists hope to uncover a theory that unites the two, a single language of the universe that applies to both galaxies and atoms. Even though black holes seem like cosmic endpoints, they are also beginnings. The material that spirals into them releases enormous energy before vanishing, radiating heat, light, and particles back into the cosmos. This energy influences the birth of stars, the movement of galaxies, and even the chemical evolution of space. What falls into a black hole is not lost, it is transformed. Through this cycle, black holes remind us that creation and destruction are not opposites, but partners, two expressions of the same universal rhythm. When two black holes exist in a binary pair, their relationship is governed by gravity's most graceful mathematics. They orbit one another in a slow spiral that may last millions of years, gradually losing energy through gravitational waves. As the orbits tighten, the pair begins to move faster, drawing closer until they finally merge into a single, larger black hole. For a brief instant, the amount of energy released as ripples in space-time exceeds that of every star shining in the universe. Yet the event makes no sound and no flash that human eyes could see. Only the faint stretching of space itself, felt across billions of light years. Some of the most luminous objects ever recorded are called quasars, powered by black holes feeding at extraordinary rates. In their centers, magnetic fields twist and reconnect, channeling matter into thin jets that shoot out from the poles at nearly the speed of light. These jets pierce through surrounding gas and radiate across the electromagnetic spectrum. From Earth, we detect them as radio and X-ray sources that flicker with rhythmic precision. Despite their violence, the processes that create quasars obey the same physical laws that govern a falling apple: gravity acting on mass, energy converted into motion. A smaller cousin of these cosmic beacons is the microquasar. These systems occur when a stellar mass black hole feeds on a nearby companion star within our own galaxy. Scaled down from the colossal quasars at galactic cores, they nonetheless reproduce the same physics: accretion disks, magnetic fields, and relativistic jets. Because they are closer to us, astronomers use them as laboratories to study the mechanics of jet formation in real time. Microquasars remind us that the grand patterns of the universe repeat themselves at every scale, from the galactic to the local. Sometimes an unfortunate star wanders too near a supermassive black hole. The difference in gravity between the near and far sides of the star stretches it into a long filament, an event known as tidal disruption. The star's gases spiral inward, glowing brightly as they are torn apart, creating a brief flare visible across intergalactic distances. What once took billions of years to form, a stable fusion engine of light, is unraveled in days. These events are reminders that gravity is both sculptor and destroyer, reshaping matter into new forms and feeding the cycle of energy that sustains the cosmos. Gamma-ray bursts are among the most intense flashes of energy ever observed, and many are linked to black hole formation. When a massive star collapses, its outer layers fall inward while jets of radiation burst outward, piercing the star's envelope and racing through space. For a few fleeting seconds, a single gamma-ray burst can outshine all the stars in the visible universe. Although they are distant, their afterglows allow scientists to trace the birthplaces of black holes and to study the early universe. Each burst is both a death and a beginning, a signal marking the transformation of a star into pure gravity. Beyond the massive black holes we can detect, physicists have speculated about tiny ancient ones called primordial black holes. These would have formed in the first moments after the Big Bang, when density fluctuations could have caused regions of space to collapse under their own weight. If they exist, they would be smaller than mountains, yet heavier than entire planets. Over billions of years, most would have evaporated through Hawking radiation, but some could still drift silently through the galaxy. Their detection would link the physics of the early universe to the mysteries of quantum gravity. Stephen Hawking's realization that black holes emit radiation changed our understanding of them forever. Before his insight, black holes were thought to be completely black, absorbing everything and releasing nothing. Hawking showed that quantum effects near the event horizon allow pairs of virtual particles to separate, with one falling in and the other escaping as radiation. This process slowly reduces the black hole's mass over unimaginable time scales. The discovery united the laws of thermodynamics, quantum theory, and relativity in a single elegant prediction, and reminded us that even perfect darkness glows faintly when viewed through the lens of quantum physics. The idea that information might be preserved on the surface of a black hole, encoded in tiny quantum fluctuations, led to the concept known as the holographic principle. It proposes that everything within a volume of space can be represented on its boundary surface. In other words, reality itself might be a projection of information stored on a cosmic screen. While still theoretical, this principle has inspired new directions in physics and philosophy, suggesting that the universe could be fundamentally informational rather than purely material. Black holes, once symbols of finality, have become keys to understanding existence at its most abstract. Entropy within a black hole follows a rule unlike any other system in nature. It increases not with volume, but with surface area. As a black hole grows, its event horizon expands, and with it, the capacity to store information. This relationship between area and entropy hints at a deep link between geometry and thermodynamics. It suggests that the shape of space itself contains energy and information, a bridge between the tangible and the conceptual. Each increase in size is like adding pages to an invisible book, recording the story of everything that crosses the horizon. The search for a unified theory, one that joins quantum mechanics with general relativity, often centers on black holes. They are the ultimate testing grounds for ideas about space, time, and information. Physicists study their mathematics not merely to understand black holes themselves, but to uncover the principles that govern the universe. Through them, we learn that nature's most extreme environments follow the same rules that define atoms and galaxies alike. Every observation, every equation brings us closer to a single elegant truth, that the cosmos, in all its vastness and complexity, is connected by patterns that never break. Black holes serve as nature's most powerful laboratories for testing the boundaries of physics. They allow scientists to study gravity, magnetism, temperature, and quantum behavior under conditions no human-built machine could ever reproduce. Every observation near a black hole is an experiment in extreme physics. By measuring how light bends, how time slows, and how matter behaves near the event horizon, astronomers gather data that refines our theories about reality itself. What once seemed abstract, numbers and equations, becomes alive in the shimmering disks and flickering X-rays of the cosmos. Each discovery is a reminder that the universe remains the ultimate teacher. Through the study of black holes, researchers have come closer than ever to understanding the elusive theory of quantum gravity, the long-sought bridge between the infinitely large and the infinitely small. General relativity describes the curvature of space and time, while quantum mechanics explains the behavior of particles and forces. But inside a black hole, both must coexist. The singularity, where matter collapses to infinite density, cannot be described by either theory alone. Somewhere within that paradox lies the key to a unified understanding of the cosmos, a single law that governs all scales of nature. Black holes also play a philosophical role in science. They challenge the way we think about limits, about knowledge, and about observation itself. We cannot see beyond the event horizon, no matter how advanced our technology becomes. This boundary is not just physical, it is conceptual. It marks the line between what can be known and what must remain a mystery. For many scientists, that mystery is not frustrating, but inspiring. It reminds us that curiosity thrives in the unknown and that the edges of understanding are where discovery begins. The singularity at a black hole's center represents one of the deepest mysteries of modern physics. In theory, it is a point where density and gravity become infinite, and the laws of nature cease to operate. In practice, it is a signal that our equations are incomplete. The universe likely hides its infinities behind a veil of quantum effects we have not yet fully described. Perhaps the singularity is not a true point, but a dense, fluctuating region where time and space themselves dissolve into a new form of reality. The study of this frontier will shape the physics of the future. In art, literature, and culture, black holes have become symbols of mystery, fear, and transformation. They appear in novels as gateways to other universes, in paintings as metaphors for the unknown, and in music as echoes of cosmic silence. Yet beyond fiction, their true nature is more beautiful than terrifying. They are not voids, but the culmination of physical laws, working with perfect precision. To understand them is to appreciate the order within chaos, the elegance within destruction. Through the lens of science, black holes become poems written in gravity. The idea that information might never truly disappear within a black hole has reshaped our understanding of existence. If the holographic principle is correct, then everything that falls in, every particle, every pattern of energy, leaves an imprint on the surface. This would mean that the universe itself is a vast network of recorded interactions, preserving history at the most fundamental level. Such a concept blurs the line between matter and memory, suggesting that the cosmos is both physical and informational. The act of observation, in this sense, becomes a way of reading the universe's endless archive. Beyond pure science, black holes inspire a sense of humility. They remind us that human life occupies a narrow slice of time and space. The forces that create and sustain these cosmic giants operate on scales beyond comprehension, millions of light years, billions of years, unimaginable masses. And yet, from a small planet orbiting a modest star, we have learned to measure them, to describe them with mathematics, and to visualize their shadows. The contrast between our fragility and our capacity for understanding is perhaps the most astonishing fact of all. In recent decades, black holes have also become tools for exploring cosmology, the study of the universe as a whole. By observing how they form, merge, and evolve, scientists can trace the growth of galaxies and the distribution of matter throughout space. Black holes help map the invisible scaffolding of dark matter and reveal how energy flows through the cosmic web. They act as markers of cosmic history, recording the conditions of the universe at different times. Each observation of a distant black hole is also a glimpse into the past, a snapshot of the cosmos when it was young. Some theories suggest that black holes could even be linked to the origin of new universes. In these speculative models, the singularity within a black hole might serve as the seed for another expanding cosmos with its own laws of physics. Our universe, in turn, could have emerged from the interior of another black hole in a larger reality. While unproven, the idea captures the imagination, an infinite nesting of realities, each born from the collapse of another. It suggests that creation and collapse are not opposites, but phases of the same eternal cycle. At the largest scales, black holes influence the architecture of the cosmos itself. Their energy output regulates the growth of galaxies, shapes intergalactic gas, and sets boundaries for the formation of stars. Without them, the universe might look entirely different, less structured, less stable, perhaps even incapable of supporting life. In this way, black holes are not merely destructive forces, but essential participants in creation. They are nature's regulators, balancing light and darkness, order and entropy, silence and motion, in an endless cosmic rhythm. In many ways, black holes represent the ultimate recycling system of the universe. Matter that once composed stars, planets, and clouds of gas does not simply vanish when drawn in. Instead, it is transformed, its energy radiated outward through heat, light, and gravitational waves. The atoms that fall into a black hole become part of a new balance, influencing the birth of future stars and galaxies. What we perceive as destruction is, in cosmic terms, continuation. Every collapse contributes to the renewal of the cosmos, ensuring that energy forever circulates through the endless fabric of existence. Even in apparent silence, black holes are never completely still. The space around them vibrates with subtle fluctuations, a restless hum born from quantum uncertainty. These fluctuations, though invisible, reveal that emptiness itself is alive with possibility. Particles and antiparticles flicker into existence and vanish again in moments too brief to measure. Near the event horizon, this restless quantum sea becomes a field of interaction, giving rise to phenomena like Hawking radiation. The very boundaries of a black hole breathe with the rhythm of physics at its most fundamental scale. When we look at the sky, we see stars, nebulae, and galaxies, but black holes are the unseen threads binding this cosmic tapestry together. They provide structure to galaxies, stability to their centers, and balance to their growth. Without the influence of supermassive black holes, spiral galaxies might lose their graceful arms, and elliptical ones might scatter into formless clouds. Their presence ensures order amid vastness, guiding the dance of celestial bodies across billions of years. They are the quiet architects of the universe, shaping everything while remaining unseen. One of the most fascinating aspects of black holes is how they bend light itself. This effect, called gravitational lensing, occurs when light from distant stars passes near a massive black hole and curves around it. To observers on Earth, this can create arcs, rings, or mirrored images of faraway galaxies, natural optical illusions written by gravity. These distortions allow astronomers to study objects too distant or faint to be seen otherwise. Black holes, by bending light, act as lenses that let us peer deeper into the universe than would otherwise be possible. When galaxies collide, their central black holes begin an intricate dance, spiraling toward one another over millions of years. This cosmic waltz releases gravitational waves that ripple across space-time, carrying the story of their union to the edges of the cosmos. Eventually, the two merge, forming a larger and more massive black hole at the heart of the new galaxy. Such mergers are among the most energetic events in existence, yet they unfold in silence. No explosion, no flash, only the slow curvature of reality itself. They remind us that the universe's greatest transformations often occur quietly. Astronomers once believed black holes were rare, but now we know they are abundant. Stellar remnants of long-dead stars likely number in the hundreds of millions across the Milky Way alone. They drift unseen, their presence revealed only when they pass in front of background stars or interact with nearby gas. These invisible wanderers may influence planetary systems, trigger bursts of radiation, or shape star clusters. Though hidden from view, their gravitational fingerprints are everywhere. The night sky, tranquil and vast, is woven through with their silent motion. As technology advances, our ability to study black holes deepens. Telescopes equipped with interferometry now link observatories across continents, capturing details once thought impossible. Future missions may use arrays of satellites orbiting the Earth or stationed in deep space to observe black holes even more precisely. Each new image, each spectrum of light, adds texture to our understanding of these cosmic enigmas. It is a reminder that even the darkest places can yield knowledge when approached with patience and curiosity. The universe rewards quiet observation, the same way the night rewards stillness. The connection between black holes and dark matter remains one of the most profound puzzles in astrophysics. Some theories suggest that the two phenomena may be related, that dark matter particles could influence black hole growth, or even that dark matter itself might collapse into black holes under the right conditions. Others speculate that primordial black holes could account for a portion of the universe's dark matter. Though no definitive evidence yet exists, the possibility that two of the cosmos' greatest mysteries might share a single origin is a tantalizing thought. It invites us to consider that what is hidden might also be united. In the most distant reaches of space, light from ancient quasars continues to travel toward us, crossing billions of years before reaching our telescopes. These signals tell the story of black holes that formed when the universe was young, only a fraction of its current age. Their brightness reveals that black holes were already shaping the cosmos long before our galaxy was born. Each photon arriving at Earth tonight began its journey before the sun existed, before the Earth cooled, before life began. In every flicker of that light, we glimpse the deep time of the universe. Ultimately, black holes remind us that the universe is both infinite and interconnected. They are born from dying stars, but their energy influences future generations of light. They bend space, stretch time, and challenge our understanding of what it means for something to exist. In their silent depths, we find the unity of all forces, gravity, motion, energy, and time woven into one seamless whole. To study them is to study the soul of the cosmos itself, a vast, elegant mystery that humbles the mind and awakens a quiet sense of wonder. The concept of the event horizon, the invisible boundary surrounding a black hole, is one of the most elegant ideas in all of science. It marks the point where escape becomes impossible, where light itself bends inward and never returns. Yet it is not a physical surface. It has no substance, no texture. It is purely a property of space and time, a threshold defined by geometry. This invisible shell separates what can be known from what lies beyond comprehension. It is the universe's quiet whisper, saying, "Here is where knowledge ends and mystery begins." In the space surrounding a black hole, gravity's grip is not uniform. Closer to the event horizon, it grows stronger, creating intense tidal forces. If an object were to fall in, the difference in pull between its near and far sides could stretch it into long, thin strands of matter, a process known as spaghettification. Though the term sounds whimsical, it describes one of nature's most dramatic transformations. In the end, matter is reduced to its most fundamental particles, absorbed into the dark, where it becomes part of the black hole's story, an eternal chapter written in gravity's script. Light behaves strangely near a black hole. When it tries to escape from the powerful gravity well, it loses energy, becoming redder and fainter. This process, called gravitational redshift, means that even photons, Particles that normally travel at the ultimate cosmic speed limit feel the influence of gravity's hand. From a distance, the light emitted near the event horizon seems to slow, fade, and finally vanish. Yet, to the matter emitting it, the process happens normally. It is another reminder that perspective shapes reality, and that even time itself flows differently depending on where you stand in the universe. Black holes may seem eternal, but they are not immortal. Over eons, they slowly lose mass through the faint trickle of Hawking radiation. For the largest black holes, this process takes far longer than the current age of the universe. But for smaller ones, the evaporation would happen more quickly, ending in a final burst of energy. When the last black holes vanish, trillions of years from now, the universe will fall into darkness and silence. Yet even then, their legacy will persist. The structure of galaxies, the spread of matter, and the story of creation, all bearing their mark. The shadows of black holes, as captured by telescopes like the Event Horizon Telescope, are not the holes themselves, but their effects on light. The bright ring around the shadow is made of photons orbiting at near light speed, twisted by gravity into a glowing halo. This ring is a boundary of perception, the point where light is balanced between escape and capture. Seeing it for the first time in 2019 was like witnessing a myth become real, the first direct image of something once thought forever hidden. That faint circle of light proved that imagination and science often converge at the same horizon. Some scientists suggest that black holes could be the universe's ultimate storage devices. Because of their immense capacity to contain information, they might hold the detailed record of everything that has ever fallen in. This leads to the intriguing notion that, in principle, nothing is truly lost, that the data describing every atom and every photon still exists, encoded in the fabric of the event horizon. If this idea proves correct, it would mean that black holes are not destroyers, but cosmic librarians, preserving the memory of existence itself in a form beyond human comprehension. The existence of intermediate mass black holes, those between stellar and supermassive size, has only recently been confirmed. For decades, they were theoretical, the missing link between collapsing stars and galactic giants. Their discovery has filled a gap in our understanding of cosmic evolution. These middleweights, often found in dense star clusters, may represent the building blocks that grew into the colossal black holes at galaxy centers. By studying them, scientists can trace the evolutionary chain of gravitational growth, from the death of a single star to the birth of a cosmic empire. In 2022, astronomers captured the shadow of Sagittarius A, the supermassive black hole at the heart of our Milky Way. Unlike the M87 black hole, which feeds actively, Sagittarius A is quiet, occasionally flickering with soft bursts of energy. To image it, telescopes across the globe had to synchronize with atomic precision, observing the galactic center for many nights. The final image, a glowing ring of light around darkness, was not just a picture, but a symbol, proof that humanity can see into the deepest shadows of the universe with patience, cooperation, and imagination. In the far future, long after the last stars burn out, black holes will dominate the cosmos. They will remain as the final structures of gravity, absorbing stray particles, radiation, and the remnants of ancient suns. Over unimaginable timescales, they too will fade through evaporation, releasing their stored energy into the expanding darkness. This period, sometimes called the black hole era, will mark the final chapter of a luminous universe. Even then, the principles that created them, gravity, motion, and the conservation of energy, will continue to echo silently through eternity. Black holes teach us that endings and beginnings are illusions. The collapse of a star gives rise to a black hole, which in turn shapes galaxies and ignites the birth of new stars. In their destruction lies creation, In their silence lies energy. They demonstrate that the universe thrives on transformation, that what vanishes in one form reappears in another. To contemplate a black hole is to look into the cycle of existence itself. A cycle without end, without beginning, only change, woven seamlessly into the endless rhythm of space and time. In the earliest moments of the universe, long before galaxies formed, black holes may have been among the first structures to emerge. Regions of slightly higher density collapsed under their own gravity, forming miniature singularities that influence the flow of matter around them. These primordial black holes, if they exist, could explain mysteries like dark matter and the early clustering of galaxies. Their formation shows that black holes are not just endings but also beginnings, perhaps the first architects of cosmic order, shaping the stage for everything that would follow. Black holes are also nature's most efficient engines. When matter spirals into them, it releases energy with an efficiency unmatched by any other known process. Up to 40% of the infalling matter's mass can be converted into radiation, far greater than the less than 1% produced by nuclear fusion inside stars. This efficiency means that the brightest lights in the universe, quasars and active galactic nuclei, are powered not by creation, but by collapse. The deeper the gravity well, the more fiercely it shines before the darkness claims it. Inside the swirling accretion disks that surround black holes, matter experiences temperatures of millions of degrees. At these extremes, atoms break apart and magnetic fields twist and snap like invisible whips. The resulting radiation travels across the universe, carrying with it the signature of chaos turned into beauty. These glowing disks are fleeting. Once the material crosses the event horizon, it vanishes forever. Yet, in its final moments, it illuminates the cosmos, turning destruction into art, a light show born from the gravity of silence. Although black holes seem far removed from human life, their influence may extend even to our existence. By regulating star formation, they shape the environments where heavy elements, the building blocks of life, are created and distributed. The stability of galaxies, the patterns of cosmic evolution, and even the formation of planetary systems are all indirectly guided by their presence. Without them, the universe might be too chaotic or too dim to nurture complexity. In a quiet way, every breath we take is linked to the gravitational balance maintained by black holes. The study of black holes has redefined what it means to see. We cannot observe them directly, yet we infer their existence through the movement of light, the bending of space, and the trembling of gravity itself. Their discovery required us to look not for what is visible, but for what is missing, to interpret shadows as evidence. This shift in thinking mirrors the progress of science itself. We advance not only by observing the obvious, but by daring to imagine what lies beyond perception. The darkness becomes a form of light when approached with understanding. When scientists record gravitational waves from merging black holes, they are capturing vibrations in the very fabric of reality. Each signal is a faint whisper from a distant cosmic event, a ripple that began billions of years ago, long before life arose on Earth. These waves stretch and compress space itself, passing through our planet silently, unnoticed by human senses. To detect them requires instruments of incredible sensitivity, capable of measuring movements smaller than a proton. In those delicate measurements, we hear the universe breathing, slow and deep, across eternity. The mathematics that describe black holes are among the most beautiful in all of science. Einstein's field equations, combined with the work of Schwarzschild, Kerr, and others, form a language that captures the structure of reality itself. Each symbol represents a curvature, a symmetry, a relationship between matter and energy. Reading these equations is like reading the poetry of the cosmos, precise, abstract, and endlessly profound. It is a reminder that the universe, in its complexity, can still be expressed through human thought and imagination. For all their complexity, black holes obey simple, elegant laws. They can be fully described by only three properties: mass, spin, and electric charge. This simplicity is known as the no-hair theorem, suggesting that no matter what falls into a black hole, stars, gas, or entire planets, only these three characteristics remain. Everything else is lost or transformed. This elegant reduction mirrors the tendency of nature to find simplicity within chaos, balance within variety. It is the universe's way of whispering that all complexity eventually returns to order. The paradox of black holes lies in their dual nature, both destroyer and creator, both silent and radiant, both simple and infinitely complex. They consume everything that approaches them, yet through their influence, galaxies thrive, stars are born, and the cosmos maintains its balance. They embody the tension between chaos and harmony, between the seen and the unseen. In studying them, we are also studying ourselves, our curiosity, our awe, and our endless desire to understand what lies beyond the horizon of knowing. And finally, black holes remind us of the quiet truth that the universe does not fear darkness. Darkness is not the absence of light, but the canvas upon which light is painted. Every star, every galaxy, every burst of radiation exists because the dark allows it to shine. Black holes are the deepest expressions of that truth, immense, silent, and serene. They show us that even in the places where light cannot escape, there is structure, meaning, and beauty. To gaze into them is to look into the heart of creation itself, vast, timeless, and forever at peace. As we drift toward the end of this cosmic journey, let us pause and remember the stillness that lies beyond the stars. Black holes, those silent architects of the universe, have shown us that even in the deepest darkness, there is purpose. They are not voids, but symphonies of physics, gravity, and time, performing a dance that never truly ends. Around them, galaxies turn, stars are born, and light itself bends into spirals of beauty. They remind us that the universe is not chaos, but harmony, a vast, delicate balance where even destruction becomes creation. When we look at the night sky, we see only the faint glow of what is near, yet beyond that, unseen and eternal, lie these guardians of the cosmos. They do not demand attention, they do not shine, yet their quiet influence keeps galaxies whole. The same laws that govern their immense gravity also hold our world together. The atoms in your breath, the heartbeat in your chest, all linked through the invisible thread of space-time. You are, in every sense, made of the same universe that creates black holes. So, as your thoughts slow and your eyes grow heavy, imagine drifting among the stars, past the warm light of suns, through the soft glow of nebulae, and into the calm shadow where gravity whispers. There, everything is silent, time stretches, light softens, and the boundaries between self and cosmos dissolve. You are no longer separate from the universe, you are part of its story, endless, peaceful, and free. Thank you for joining this journey through the most mysterious and beautiful forces of existence. If this calm exploration helped you find peace tonight, consider subscribing to Sleepy Scientist, where each night we drift deeper into the wonders of space and science. Until next time, may your dreams be quiet, your thoughts be weightless, and your sleep as deep as the stars. Good night.